So what do I do now? Do I connect to what? Ah. Okay. Yeah, okay. So this is a joint work with Matteo Campanelli and Dario Fiore. And okay, so in general in this talk, I will talk about provable security for certain types of cryptographic primitives, like a certain design paradigm, and specifically about when you compose primitives that are secure in the AGM, when you compose them with snarks, how do you prove security for those? And one key takeaway would be that this technique would allow you to unlock new instantiations for unbounded depth IVCs that can be built from a larger class of snarks and folding schemes that was not possible before. So by unbounded depth, I mean that this incremental computation can go on for like arbitrary polynomial number of steps. So this is what these are the type of protocols I'll be talking about. So composite protocols where there's like this inner primitive, primitive X, and then you put a snark on top of it to get the composite primitive Y. And the reason you might want to do this is that X has some properties and you want something extra, so then you put a snark on top to get those because it's a very general purpose primitive. And it is used in, like, this type of design is really used in many places. So for example, you can use it to compress proofs or batch proofs where you have several snarks in the first layer that give you this vector of big pi. And then you don't want to send all of them out, so you compress them using another snark on top, which just proves that all of these input proofs verify. Another example is a folklore construction of aggregate signatures, where again you have several signatures, and instead of sending them all out, you put a snark on top to aggregate them. And something that has been more relevant these days is incrementally verifiable computation, which is essentially the same as example one, but it's like several steps of snarks composed on top of snarks. Okay, so how do we prove security of such primitives? Intuitively, like what we want to say is that if the snark is knowledge sound, which is the most basic security definition for snarks, and if this underlying primitive X is secure for whatever definition, for whatever relevant definition, then that should imply security for Y. And you would prove this by building a reduction, which would be like, okay, so for contradiction, let's assume there's an adversary against primitive Y who outputs this final output, little pi. And so because this is actually the output of the snark component, I could then build an adversary that has given access to the adversary Y, which then this would be an adversary against a snark. So therefore, by knowledge soundness, there should be an extractor, and I can extract the previous input, W. And now this is an output of primitive X. So I can build an adversary X. And because I assume that primitive X is secure, therefore this should not be possible. But an issue here is that when this underlying primitive X is secure in the algebraic group model, then this reduction wouldn't work. So before I explain what the issue is, I'll motivate a bit more why we consider the AGM. The reason is very simple. It's a very popular and common model to prove security of many cryptographic primitives, and especially for proving knowledge soundness for snarks, special types of snarks that are very efficient. For example, oh, wrong spelling, sorry. Grad 16, Planck, Lunar, etc. These are all constant size snarks, and they're proven in the AGM. Another reason is because AGM allows you to have a special property from extraction called straight line extraction. And this, I'll talk about it later, but this is very essential for getting unbounded depth IVCs. So using this property, for example, what we can get is like proof systems such as bulletproofs or folding accumulation schemes like NOVA, which already have knowledge soundness under a different model. For example, they have proofs in rewinding. With AGM, we can get straight line extraction for these protocols. And so then when we build IVCs on top of these, we would get unbounded depth IVCs, like provably secure unbounded depth IVCs from such primitives. And finally, AGM is like quite strong, so it can also be used for, it is used for proving advanced properties for other primitives, for signature schemes. For example, to show instantiations of blind signatures, multi-signatures, they can be proven in the AGM. Okay, so again, like just a brief, what AGM is. It's a model where we assume that the adversary gets some input group elements, G1 to Gn, and then it outputs Y, which is also a group element. Then we assume that it should give us this vector gamma 1 to gamma n, which explains how it computed Y given the initial group elements. This is the example from before, and I want to try and prove, like show you what the issue is when composing in the AGM. So here again, like layer 1, there are a bunch of CRUD16 proofs that are then compressed or aggregated using a layer 2 of another CRUD16 proof on top. So to prove it, well, first there's this adversary against the full scheme who gives you the final proof, little pi, and because it's algebraic, it also gives you group representations, gamma, this gamma vector. So we can apply, we assume that CRUD16 is secure against algebraic adversaries, so we can apply the extractor using both of these inputs to extract the previous input, which is this capital pi, the vector of all proofs. Now ideally we would define this as an adversary against the layer 1 of CRUD16, and then potentially invoke the extractor again to extract the initial inputs. However, here this adversary needs to be algebraic, and so the adversary that we define, it's not a valid one. And really that can't happen because when we apply this layer 2 extractor, it wouldn't know the group representations. So it can't give us that, and we can't build a valid reduction. So yeah, so then like putting it all together, the issue is when we try to do this reduction and we want to reduce it to security of primitive X, we need to build an algebraic adversary, and we can't do that. Right, so the next thing I'll discuss is, well, how to solve this thing. Okay, so the idea is pretty simple. This is the slide from before, the layer 1 snark and the layer 2 snark. And here layer 2 snark is proving whatever it's proving that I'm signifying here with this circuit C. So the idea is, okay, so this is the actual output, pi 2. If I could just output even the intermediate proof, pi 1, directly, because it's an algebraic adversary, it would give me all the representations I wanted, so I can do the reduction. But of course, you don't want to output it explicitly. So then the idea would be to force the layer 2 prover to output this pi 1 in query it to the random oracle, so that we see it somewhere, but not explicitly as a part of the output. And then we would change the AGM model slightly. We would say that, okay, now the adversary also has access to the random oracle, and whenever it queries the random oracle with some group element, it is also telling me the representation. So in addition to an explicit output, explaining an explicit output, it also explains its oracle transcript. So now we can recover all the representation we wanted just by looking at the random oracle transcript. And this proof will never appear in the final output. Right, so concretely, this is the layer 2 snark prover, and we'll just add this additional step where it needs to process the input Z1 and pi1, extract the group elements from this, and query it to the random oracle. And then we change the circuit C slightly to C star, where it also proves that these responses are actually coming from the random oracle. And then to do the reduction, so this is pi2 is the actual output of the composite protocol. And in addition to this, we get the transcript of the random oracle, which is this TR arrow. And because it's an algebraic adversary, we also get this gamma, which will have the group representations for both pi2 and any group element that's present in TR arrow. So just applying the extractor, we will get the previous input. And now, because of how we define the modified circuit, we know that both of these inputs, Z1 and pi1, can be found in the transcript, the random oracle transcript. And because of the new modified assumption, the group representations for this can be found in this gamma. And now you can invoke the extractor again and do your reduction. Okay, so now I want to talk why this is helpful for IVCs and getting unbounded depth IVCs. Just a little bit a background about IVCs. So they are special proof systems that allow you to prove proofs for streaming computation. So you have some function f that's applied a number of times to get your final output Zn. And IVCs would allow you to compute a proof for this in an incremental fashion. So first you'll compute the proof for just the first part and just propagate pi1 to the next step till you get the last proof pi(n). And the property that the security property we want here is a version of knowledge soundness where the extractor is basically asked to extract every intermediate state. So all Z1 to Zn minus 1 and all the witnesses W1 to Wn. And this is different from Snark's extractor, which only extracts one thing at a time. Right, so a very common practical way of building IVCs is through recursive composition of Snarks. So you have step I. What we do is we define a recursive circuit, which consists of two components. The first component just proves that this function f for step I has been computed correctly. And the second component basically checks this snark proof pi I minus 1. So this circuit at step I basically says that, okay, this current step is done correctly, and everything till step I minus 1 was done correctly. In general, you don't need to use an argument system, a full argument system to do this, this construction. What you can use are slightly weaker primitives called accumulation schemes or folding schemes. And they're nicer because they're very lightweight. So your IVC construction is better. And right, so the prover gets these previous step outputs and the local witness Wi. It will compute the function for step I. And now it has all the inputs to invoke the argument or snark prover on this recursive circuit and get the proof for this step. The IVC verifier is very simple. It just checks the last proof that comes out. And because at every step we guarantee that all the steps before this have been done correctly, it's enough to check the last proof. Okay, so right, just to mention, so now if this argument system that we're using to build the IVC, if it was secure with AGM, it would have the same problem that I just talked about before. So we can fix it by changing the prover by, again, adding this component, making it query the group element explicitly, and then changing the recursive circuit to prove the correctness of this query. And the important thing here is that now, because the extraction can just work by looking at the previous extractor's output, like the important thing here is that the extractor never needs to call the prover, the adversarial prover again. It's invoked once, and you get Z0, Zn, pi n, and now you just keep extracting from that. You never call the adversary again. And this is important because it gives you the following bound. It tells you that the soundness of the IVC scheme will be upper bounded by n times the soundness of the underlying snark. This means that well, n here is the number of times you repeat this computation, so the depth of the computation. So this means that n can be like arbitrary polynomial in the security parameter. And to put it in the context, usually if we want to prove the security of IVC, what happens is that it blows up exponentially in the depth, and the security, the soundness error of the underlying snark, which means that most of the time it's only secure for constant depth. But what we want in practice is that we can keep using it for arbitrary depth. And just to point out here, there has been a previous work that tries to circumvent this limitation of exponential blow-up, but it is only applicable for proof systems that are derived from interactive oracle proofs, and they don't really work for these AGM-based snarks. So here, what we will get is that we can now apply, like, get IVCs from these other types of proof systems. What is this? Oh yeah, I didn't. One thing that I didn't like really mention so far is like we're proving this random oracle inside the circuit, and so how do we do that? And again, the whole thing is that we want provable security. So this is an important question to answer. Here we use something called as relativized arguments or snarks. These are special types of snarks that are able to prove statements about oracles. And we know that we can't have relativized snarks for random oracles. So what you need is a certain, like a variant of random oracle that is very, like it's similar, but it has more structure. So it allows you to prove these statements. And some examples in the literature are these signed ROM and arithmetized ROM. And among these, the arithmetized ROM is like particularly interesting because it allows you, like it gives this generic lifting result where it says that if your underlying snark has some property in the ROM, when you replace the ROM with a ROM, it will also, this property will also be preserved. So essentially, if it was knowledge sound, it's still knowledge sound, and zero knowledge, then it's still zero knowledge. This is nice because you can just take any snark that works in the random oracle and then have a relativized version that works in AROM. You don't need to redo any sort of analysis to use this snark. Okay, so concretely, our theorem says you need to use relativized snarks for some oracle O, and we can use arithmetized ROM, for example. And if this snark is straight line extractable in the AGM and this oracle, then the IVC scheme that you build from this will be secure for arbitrary depth recursions. Okay, so before I wrap up this talk, I want to talk about other works that exist to basically resolve the same problem with AGM composition. So there's this work which defines a different AGM model called recursive. Well, they don't call it recursive AGM, they call it extended AGM, but I'm calling it recursive AGM. And it's a stronger version where it says that, so this is the usual AGM definition I have here. And in addition to this, it says that if any subset of this representation, group representation, so for example, gamma 1 and gamma 2, if they satisfy some predicate, this F lab, then that should also be explainable. So what this means is that if gamma 1, gamma L can be interpreted as a group element, if it's possible to encode it as a group element, then the adversary should give me representation for this too. And then, so it should give me gamma, and then if this itself can be, like if there's something in this latest gamma that can be encoded as a group element, then you should give me representation for that too. So it just keeps going on all the way to the last level of the recursion. As opposed to what we use in this work, which is like really the basic AGM with a random oracle attached on top of it. Apart from this, like this assumption, when you look at the definition, apart from it being new and also more complex, the issue is that this condition that, okay, if I look at this representation and if it can be interpreted as a group, then give me representation for that as well. This is quite protocol dependent. Like this function F lab or this predicate F lab really depends on the protocol that you're trying to analyze. This means that when you change your protocol that you're trying to, that you want to prove secure, the algebraic assumption would change. However, like in our case, it's like the assumption is very well defined. It's clear what is to be explained. It doesn't change with every protocol that you want to analyze. One interesting connection could be that what we do here, this technique is in a way, it is forcing this recursive behavior. Because it's forcing the prover to explain all these intermediate things. So it is a way of like having this recursive AGM concretely. A benefit of this recursive AGM assumption, and one reason why it was introduced, was because you don't need to change the protocol in any way. This is a much stronger assumption, and it allows you to prove security of schemes without changing them. So on the other hand, a downside of this technique that I just talked about is that you have to use relativized snarks, and they require you to modify the snark to adapt it to this other oracle. And so this construction that we will have here will be more heavyweight than if you were to use recursive AGM. So to summarize, I showed a very simple technique to get to prove security of composable, primitives that are formed by composing AGM secure primitives with snarks. And this has applications to unbounded depth IVCs and other primitives like aggregate signatures. And concretely, this gives us new instantiations for provably secure IVCs from proof systems like Growth 16 and folding schemes like Nova. And finally, one open question that we can think about is that this, what we did in this paper was a very general, like we just assume a general circuit that can take care of group operations. However, what we would do is probably something like cycle of curves to implement IVCs. And it would be important to see concretely what happens when you use this. So for example, one thing that would happen is that you would have two parallel IVC chains that has to be now linked together when you do this computation. Another question that I didn't really have time to discuss much, so I'll just talk about in a high-level way, we have a result for showing, for proving a security of aggregate signatures, where signatures are secure in the AGM. And this requires special snarks called oracle snarks. And these are basically snarks that are secure in presence of arbitrary oracles or signing oracles. And in the paper, we show a very specific case. We show that KZG commitment scheme is secure in the presence of specific signing oracles, such as for BLS and Schnorr. So it would be interesting to see what generic properties you wouldn't want from signatures and commitment schemes to get like generic OSNARKs. Okay, yeah, that's it.
Any questions for Mahak?
So this construction, if I understand correctly, required changing the circuit to query the random oracle. Is that right? Does that run into concerns about soundness of fiat shamir when the circuit references the oracle?
I think so. First, like you can have an idealized, like you do have a provable security in some model, which is like this AROM, arithmetized ROM and such. And it's true, when you heuristically instantiate this with an actual hash function, there might be similar problems as we see in like fiat shamir attacks. Matteo?
So no, we're not in the circuit. We're not proving that we're querying the random oracle, and it's actually not the random oracle. It's so what you do, you prove something else in the circuit. So you're basically folding and deferring something that eventually is going to be at the end something about a random oracle, and then at the end the verifier is going to be like, okay, let me query the random oracle at the end. So at the end of the the unfolding, yeah.
Maybe you should discuss this offline, but is it something that's much cheaper than the actual hash function?
I don't remember, but it isn't. So the question to do you incur into problems for fiat shamir? The answer is no. This is also from a previous technique by paper by Alessandro and others. And the other question I don't know, and we can take it offline. And maybe yeah.
Okay, I don't think we have time for more questions, so let's thank Mahak again.